This is lecture number 20, and it's a continuation of chapter 7. We have already studied electro-optic modulator and acousto-optic modulator, and in this chapter uh, first we study about the cavity damping and then mode locking. Cavity damping. What exactly cavity damping? You have this cavity, okay, these are mirrors, okay, and you are using electro-optic device here. This is your laser medium and this is a beam splitter. In cavity damping we also use the electro-optic device or acousto-optic device technique. Definitely it's a Q switching technique as well, whether to use a simple electro-optic devices like we have explained, or to use with a beam splitter. So in this case you don't need to put any kind of polarizers around like in case of electro-optic modulator, if you use only electro-optic modulators. And when it's not energized, it's off, the electro-optic device, electro-optic pocket cell, then you can see the beam is passing through, okay, and population inversion is building up. It's like in the normal way. So the one thing actually I would like to explain here, in this kind of cavity damping technique, you don't use a partially reflecting mirror here. Both are fully reflected. Okay, these both are fully reflected mirrors, and the light is actually deflected from the beam splitter which we are using inside the cavity. Okay, just after the electro-optic focal cell or acousto-optic device, but mostly we use electro-optic device. So this beam splitter, it comes in between the laser medium and focal cells. So what exactly happening here after building up this one? When we turn on the electro-optic device, then uh, polarization of the light is changed. So when the polarization of the light is changed, so it's reflected from here, it's not passing from here. So we get a huge pulse. So this is, in a simple word, this is called the cavity damping technique. In actual, what exactly this mechanism or this concept was started to remove the mirror. Mechanically or with the hand or whatever it is. This concept was started like this. So remove is amplifying here, okay, and instantly you remove this mirror and you get the output. Okay, but that is purely mechanical, which is, you cannot control the way you can control with electro-optic devices, and this is not an efficient way. So this concept was started from here कि आप मिरर को रिमूव कर दें, ठीक है, whether mechanically or whether in a, but actually practically they did with using the electro-optic way. So you can, in this way you can control the pulses, the time duration, and different things. So all these things are here, it's mentioned, which I explained here, okay. Or it can work with any kind of lasers. It can be a solid state laser, or it can be a gas laser. Any laser, if it is working in a CW mode, it can be converted in this way, okay. Or to produce fast pulses up to 20 times more powerful than CW laser. So if we do this thing like on off the electro-optic device, then we can produce a train of pulses. This on off can be done with any electronic circuit, or this is basically electronic circuit, and then you can produce the produce this kind of pulses, the train of pulses repeatedly in a very fast way. It depends how you switch on and switch off. So if I try to explain in Urdu, कैविटी डंपिंग टेक्निक जो शुरू हुई थी, जिसके बारे में पहले सोचा गया था, वो ये था कि एक कैविटी हम बनाते हैं, ठीक है, कैविटी को पॉपुलेशन इन्वर्जन बिल्डअप होने दें, फिर मैकेनिकली एक साइड के मिरर को हटा दें. दैट कुड बी दिस वन, ओके. और एक साइड के मिरर को हटा दें तो उससे हमें जॉइंट पल्स मिल जाएगी, फिर उसे क्लोज कर दें. बट इन दिस वे यू कैनॉट डू इट शॉर्ट टाइम में, नहीं कर सकते आप ये चीज़ें. तो प्रैक्टिकली जो टेक्निक उन्होंने इंट्रोड्यूस कराई वो इलेक्ट्रो ऑप्टिक पॉकल सेल यूज़ करके, और इसमें विदाउट पोलराइज़र यूज़ नहीं कर रहे, सिर्फ बीम स्प्लिटर यूज़ कर रहे हैं, और दोनों साइड के जो मिरर्स हैं वो फुली रिफ्लेक्टिंग है. इसमें पार्शियली रिफ्लेक्टिंग मिरर्स इस्तेमाल नहीं हो रहे, और दोनों फुली रिफ्लेक्टिंग है. और क्या होता है कि जब पॉपुलेशन वर्जन बिल्डअप हो जाती है, जब पॉकल सेल ऑन नहीं होता, जब ऑन होता है, एनर्जाइज होता है, तो उस सूरत में हमें जायंट पल्स मिल जाती है, जो कि रिफ्लेक्टेड बाय जो आपका बीम स्प्लिटर है. क्यों? क्योंकि पोलराइजेशन चेंज हुई थी लाइट की. तो बीम स्प्लिटर जो यूज़ किया जाता है, दैट इज़ वेरी इंपॉर्टेंट. दिस काइंड ऑफ बीम स्प्लिटर इज स्पेशली कोटेड for certain kind of wavelength. I mean, it depends what kind of laser you are using, what wavelength is in use. So according to that one, this beam splitter is polished. और ये बीम स्प्लिटर जो है, ये एक पोलराइजेशन को जो है ना वो ब्लॉक कर देता है, जो कि रोटेट हो जाती है, ठीक है, और वो डिफ्लेक्ट कर देता है. दैट वी गेट ह्यूज पल्स. Here you can see this is same polarization passing through. When the polarization after here is changed, and this polarization cannot pass through here, and it's deflected from here. So this is, you can also say, as a polarizing beam splitter, in the sense there are some certain kind of polarizing beam splitters, but in normal sense we don't call it polarizer. Okay, so ये जो आपका beam splitter है वो एक polarization को गुजरने देता है, दूसरी को ब्लॉक कर लेता है. That you have to decide, okay, when you develop the laser, make the laser, or this kind of things. Now, it's a mode locking technique. Mode locking technique is the most latest in the sense that you need this technique in femtosecond laser a lot. You can also apply this technique to the other lasers, but it's more natural in femtosecond lasers. और जो दूसरी लेज़र है उसमें ये एग्जिस्ट तो करती है, लेकिन उसके लिए आपको इलेक्ट्रो ऑप्टिक डिवाइस यूज़ करनी पड़ेगी. लेकिन फेमटोसाइकिल लेज़र में नेचुरली हो जाता है. इट्स अ कम्बिनेशन विद द कैर इफेक्ट. एनीवे, इट्स टू मच बिकॉज दिस इज नॉट ए स्कोप ऑफ this chapter or lecture what we are studying. So here we will only discuss the basics of some mode locking, what is mode locking, and some basic technique, something like this. So first thing is, mode locking are used to generate shortest pulse of light. With the quasi switching technique, with the cavity dumping technique, we cannot use a very small pulse. Certain limits, within limits. Okay, you can use a nanosecond or maybe picosecond in some cases. But to produce a very short pulse, like in a femtosecond range and picosecond also actually, we have to consider the mode locking technique. These modes, what exactly these modes are? Modes are basically, these are longitudinal modes. So we lock these modes, the wave passing through, with the same phase. How to make it? There are many ways. They don't stay in phase with each other. So we want to make them pass through in a phase. This is mode locking. With the diagram, maybe in the next few slides you can see, like this is, if this is the phase here, these are in phase. Okay, if they are not in phase, like this. So basically we are locking this thing. Okay, There are two ways to look at this technique. Okay, whether we can look in a time domain or frequency domain. In time domain is very simple, but you cannot visualize or you cannot really understand what exactly mode locking is. So frequency domain is much more important, and we can understand more, I think, in frequency domain. Mode lock laser, energy in the laser itself is compressed into a single packet. Okay, that single packet in the form of pulse. These are single packets form of the pulse. Okay, traverses the light. Okay, these pulses, when it's mode locked, these pulses move in the lasing medium and pass through the cavity mirrors, partially reflecting cavity mirrors, like here reflecting from the cavity mirrors. The pulse inside the cavity is much shorter than the cavity itself. The pulse inside the cavity, definitely, if the cavity is 1 meter long, or you can say half a meter, it doesn't mean that the pulse of the laser will have the same uh, length. No, pulse always much less than the length of the cavity. Okay, so this is what I explained here. If the cavity was 1 meter long, the pulse might typically be 10 centimeter within this cavity. Might be. There are certain calculations are used for this purpose. If the cavity contains partially reflecting mirror as an output coupler, as we know already, a short output pulse transmitted each time the pulse is reflected from that mirror. So as I explained, that packets are passing through, and these packets pass through the output coupler as well when it is, or laser is, mode locked. Okay, so on this slide we can visualize the mode locking. If you see here, this is a cavity. Okay, cavity, and the pulse is moving or propagating or transversing through the cavity. Here the Q switch is closed, and here the Q switch is closed, here Q switch close and close. Now we start, when the Q switch is closed, the pulse travel through the amplifier. Okay, it's travel through the amplifier and it's reflected from here and come back. Now the pulse approaches to the closed Q switch. This is the starting point. Okay, now pulse approaching to the Q switch here, and the Q switch is closed. The next step, when the Q switch open, this pulse passes through, and from here again the Q switch is closed and the pulse move in this direction here. Now let this Q switch is open, it let the pulse to pass through, and again it is closed and the pulse is moving in other directions. Okay, pulse travels the amplifier, and from here, this is output coupler, and from here the light is coming out, the laser light is coming out. So pulse travel through the amplifier, like this. Okay, and when it comes here, the focal cell open, it pass through and then again travel. Okay, travels through the amplifier in a number of steps. After traveling through the number of steps, the Q switch is closed, so it's not reflecting from this side, but it's coming out from this side. Okay, like here. So this is how the mode locking in the time domain, you can say. Okay, but we don't exactly understand what exactly going on. So some of the points here um, is mentioned in this, according to, this figure. The mode lock laser, the mode lock laser consists of a normal Q switch laser. Okay, yeah, by sure we use a Q switch. The Q switch is opened at regular intervals corresponding to the transit time of the pulse within the cavity. open, close, open, close, open, close, open, close. Okay, this is, it depends on the configuration of the Q switch. So what it says, the Q switch is opened at regular intervals corresponding to the transit time of the pulse within the cavity. Transit time of the pulse within the cavity. Transit time of the pulse within the cavity. Okay, so this time C over 2L. C is the speed of light and L is the length of the cavity. So this time is depending on this thing. C divided by 2L. Okay. Once per round trip through the laser cavity, Q switch is opened, like here, one round trip, like this, to allow the pulse to pass. Okay. At all the other times the switch is closed to prevent any other light from oscillating the cavity except this mode locked pulse. So one time it's open after one round trip. Okay. Rest of the time it's closed and letting the pulse to get out from the output couplers. Okay, so at all the other time switch is closed to prevent any other light from oscillating in the cavity except for this mode locked pulse. Except for this mode locked pulse. All the other pulses are blocked, only this mode locked pulse will be moving. It depends on this time. Okay. Here, with the modulator in the center of the cavity, it is required to open twice for each round trip of the pulse if it is placed near the mirror in the cavity. So what it's saying here, it is required to open twice for each round trip of the pulse, this Q switch, if it is placed near one mirror in the cavity, as in the figure here, near to one mirror. It can be two mirror, double, I mean here as well possible. Only one opening of the switch is required per round trip. Here only one time switch is opened, the round trip of the pulse. Okay. So what exactly they are saying, that the Poggle is used here, electro-optic modulator, and to produce a mode lock laser pulse, and one time it opens it in this cycle, actually one time opened and rest of the time is closed, and we get only that pulse which is mode locked. Okay. So it opens only one time here. So this is how we get the mode lock pulse. Okay, one time it open in the and one round trip. Okay. Now what is written here? Some more points related to the mode locking. What it says, the output of a mode lock laser with the configuration described is a continuous series of short pulses in the previous slide. Okay, on off the Q switching. Okay. In the case of a laser with mirror 1 meter apart, 1 meter apart is the length of the cavity maybe, the pulses will appear at frequency C by 2L. Okay, or 150 megahertz. If you calculate C by 2L, it will give you the frequency which is 150 megahertz, and from frequency you can also calculate the time period. So pulse duration depends among other factors on the time for which the Q switch is open as well. Okay, when the Q switch is open, the pulse duration depends on the other factors as well, your lasing medium, your gain of the lasing medium. Okay, Q switches for a mode lock laser must open and close in a very short time period. Turning off and on is very short if you want to get a very short pulse. Okay. So C by 2L, with the help of C by 2L, you can find out the frequency and then you can calculate the time period. Now it's saying because we need a very short time to turn on and off the focal cells. So the regular Q switches are generally not very fast. Regular Q switches are generally not fast enough. Okay, जो नॉर्मल जो मार्केट में अवेलेबल होते हैं, जो नॉर्मल प्राइस में जो पोकल सेल्स, उनकी स्पीड इतनी ज़्यादा नहीं होती. But for the produced to the short pulses, especially for the mode locking, using a mode locking technique, हमें वो पोकल सेल वो चाहिए जो स्पीड से इस पे अमल कर सकें. So here now a typical modulator, it takes 100 nanosecond to turn on and off. Okay, switching time. But the total optical length of 1 meter laser is 2 meter. Total optical length, because it's a round trip time, 1 meter length, so light traveling from one mirror to another, the other mirror to the first one, that is 2 meter. Okay, so here 1 meter, 1 meter. Okay, so it will be 2 meters. So total optical length 2 meters. So light makes a round trip through the entire laser in 6 nanosecond. 6 nanosecond using this equation. So if you find out the time, that would be a 6 nanosecond. So definitely if we use this kind of modulator for the mode locking, it will not work. If we use this normal, we need this time. Otherwise useless. Okay. So what it says, in much less time than the transit time for the pulse in the, so it must be switched in much less time than the transit time for the pulse in the laser cavity. Okay, so we have to see the specification when we buy or if we make the electro-optic device or acousto-optic device, what switching speed we need and what kind of laser we are using. The previous slides we discussed in the time domain stuff. Now mode locking in the frequency domain. In the frequency domain, as I explained to you, it's much easier for us to understand. And we have to go through these points here. What it says, the time domain view of mode locking does not explain how this technique literally locks the phases of the various longitudinal modes in the laser together. As I told you, what we are locking, that is the longitudinal modes. And actually we are locking the phases of the phase of these modes. You can also call it phase locking. When considering a practical laser, okay, apparent that many longitudinal modes with slightly different frequency can oscillate simultaneously in the cavity. Yeah, obvious. Like this, like this, like this, like this, like this, like this, something like this. Okay. So what we do actually, by considering the practical laser, it becomes apparent that the many longitudinal modes with the slightly different frequencies can oscillate simultaneously in a cavity. It's obvious we cannot make such a perfect laser. So if these mode components are examined at any point in the tube, okay, these are can say it's tube. Each of these has a different phase relative to each other. As I told you, phases. Okay, phases, 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 phases. So in a mode lock laser, all of these components are locked together in a phase, which with each other. So mode locking basically is a phase locking. You are locking the phase of these longitudinal waves traveling. Mode lock pulse is moving down the laser cavity, obvious. Each component at the same speed. When it is phase locked like this, like this, like this, then all these move at the same time. Here, where these components interfere constructively, so this is the center of the mode locked pulse with a high peak power. You can see the figure later. So what they are saying, when these modes or when these components interfere constructively, so this is the center of the mode lock laser pulse, mode lock pulse. And when it interfere constructively, these components, then we get a high peak power pulse. Okay. So if there are like this and like this, when they are locked phases, it get pulse like this. You'll see in the figures. So what it's saying here, all modes in the laser are given equal amplification at the same time. All modes in the laser are given equal amplification at the same time because it's locked. When the switch is open of the the electro-optic modulator. So energy is distributed among these modes equally when it's locked. Okay, where the modes interfere constructively in phase. Okay, so the mode lock pulse peaks. Where they interfere destructively, the pulse is extinguished. Where they interfere, these phases interfere destructively, it extinguishes, it's vanish. It is not amplified. You cannot get at the output. So only you will get it when they are interfering constructively, and only they can do it when their phases are locked. Okay. Here, this is the equation. We're studying in a frequency domain. Okay. How the mode lock pulse is manifested, we are, I mean, in this book, see how the thing is explained. Consider the Fourier series of the light pulse in the cavity. Fourier series you must have studied in mathematics. And whenever we go for signal processing, we should know the Fourier series, which consists of various longitudinal modes. Okay, the pulses in the cavity, it has various longitudinal modes. We are utilizing these different modes in the cavity. We are not narrowing to avoid these modes here. We are utilizing these longitudinal modes to generate a mode locked, to have a mode locked laser and to get a high peak power pulses by this technique. So Fourier series, various longitudinal modes. Okay. So what it's saying, in most practical lasers, the bandwidth of the gain is wide enough to allow a number of longitudinal modes. The gain medium. Okay. The gain. So the bandwidth of the gain is wide enough to allow number of longitudinal modes. Okay, many longitudinal modes we have, and then we lock it and we can get a short pulse. So each of slightly different frequency to oscillate simultaneously in the laser output, as was in the last slide. A solitary laser such as Ruby or YAG will certainly allow many simultaneous longitudinal modes to oscillate. Example of Ruby and YAG. Okay, the gain medium is like that. They allow simultaneously many longitudinal modes to oscillate. So if you modeling each wave in the laser at sine wave, each wave, okay, with slightly different frequencies, each wave is a sine wave with a slightly different frequency. The amplitude output wave of the laser is the sum of amplitude of each component. Okay, so modeling each wave in a laser as sine wave, slightly different frequencies. Okay, so to get the amplitude of the output wave of these number of waves, as in these number of sine waves, we get is the sum of amplitude of each component. If you get the amplitude at the output, we get the sum of amplitude of each component of these waves. Okay, so here, 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 these are terms. Okay, and these sine waves here. What these terms are, you can see now the terms of this equation represent each component mode. Okay, each component mode. The component En sine omega and t represent a mode with the frequency omega n. The component En sine omega n t represent a mode with the frequency omega n. The component En, this component, represent a mode with the frequency. This is the frequency of this mode. There are different modes here. So En is the amplitude of the components, which follows the gain bandwidth of the lasing species. Each component of series in equation represent a component that is standing wave with an integral number of waves inside the laser cavity. These are inside the laser cavity, standing waves, okay? And these are the components here, frequency components. Now, here, n+1 components having this much standing waves, okay? This is in general, I mean, for your information. Within the cavity, the n-1, okay? n+1 and n-1 component having this much waves and so on. This is repeated in this way. Okay, n plus components, n+1 components, and then within the cavity n-1 component. So it's reducing n-1, n-2, n-3, etc., etc. Okay, but the main points, these and these here. Here you can see in this figure, there are different waves, okay, and a slightly different frequency. So what happens actually when they mode lock, then we get a giant pulse. Here is also the white and this grayish and this one black. Here they are completely overlapping each other. So this is a locked, and we get this one, this pulse. Okay, so these frequencies are summed up: F0, F1, F2. Okay, F1, F2, and F0. These are summed up, and you get this giant pulse. When these are not summed here, these are varying, like here, here, it cannot produce the giant pulse. They can only when it's locked, same phase. So the amplitude of each of these component waves is summed by interference. What does it mean? The amplitude of each of these components, these component waves, is summed by interference because they're interfering with each other. Okay, that is why you get this. When all the components waves are in phase, all the component waves in phase, constructive interference occur. Obvious. Okay, producing a large amplitude. When they are in phase, different frequencies, okay, different waves, and it means they are interfering constructively. So it means it will produce a large amplitude. Okay, summed up. That large amplitude is a wave we get more locked. So at some point, these amplitude will sum to zero at some amplitude, and resulting sum amplitude will also be zero. If they are not interfering or if they are destructively interfering, then the sum will be zero. We don't get anything extinguished. The situation is shown here very clearly, as I mentioned. They are using three individual modes. Okay, this one, this one, this one. So each with a slightly different frequency, different frequencies, each and every. Okay. Now the amplitude of all these three modes is summed here, revealing a pulse of large amplitude, this one. That result where the phases are the same. Phase, phase, phase of this one you can see same. So this is at the center of the figure. So here, this portion, when the phases, all the waves are in phase, locked, and at the end we get a large amplitude. This is a constructive interference, and it is destructive interference. It will extinguish, vanish. Okay. Here some more points. What it says, by opening a cave switch at periodic intervals, we are more locking using cave switch here. Okay. All modes in the laser are given equal amplification. We already know about, which momentarily locks their faces together. As explained, if one is going like this, other one is going like this, other one is going like this, at certain point comes when they are in phase with each other, then we get giant pulse. A fast large pulse results a mode lock pulse. Okay, fast large pulse. If the switch is opened at regular intervals at a frequency of C by 2L, as we discussed before, the pulse continues traversing through the laser and we get the mode lock pulses. Okay. Energy build in upper lasing level when the pulse is not present in that area of the laser medium. Okay. Like can happen in the cave switch. Okay. So resulting in a high gain as the pulse passes through the laser. When it's off, same thing happen, the population inversion build up. Okay. Cave switch build energy in the lasing medium. Okay. Resulting in a high gain. And when it open, then the pulse passes through the laser. As the pulse is reflected from output coupler, an output pulse results. Obvious. The output from the mode lock laser thus consists of a train of extremely short pulses. No doubt about it. A single pulse may be extracted by adding second optical switch in front of the laser. So the single pulse may be extracted by adding a second optical switch such as electrode modulator in the front of the laser. That is, I mean, different thing. I mean, if you can add another switch at the output of the laser, and that is a bit different thing, because what we are studying actually is using inside the cavity. And here we are studying to get a train of pulses, the Mortlock laser. Okay, extremely short pulse. And other option is to use a second optical switch in the front of laser. Okay, that is a little bit different thing. Okay, I don't want to make you confuse here. So better to omit this thing. Okay. Here, it's a similar kind of diagram you can also see in your book. It's an important thing which I wrote here and make it red. A laser species with a wide spectral range. A laser species with a wide spectral range will allow more modes to oscillate. A laser species with a wide spectral range. The laser medium you are using, the laser medium you are using, okay, we already studied what are the longitudinal modes. Okay, so we can eliminate the longitudinal modes by using kind of apertures. Okay, to limit the gain of the lasing medium. Okay, so if the laser medium is a wide, you can say, then more longitudinal modes will be oscillating. So if more longitudinal modes will be oscillating and we summed up, logged and sum up, then we get a amplitude, high amplitude pulse at the output and much shorter uh, duration. Wider the spectral range, wider the spectral range. Okay, wider the spectral range and we can get more shorter pulse. So spectrum, if it is like this, like 0.1 nanometer or whatever, useless. You cannot produce a more log pulse. If spectrum is little bit wider, then you can do it, and it depends on the lasing medium and the gain of the medium. And this thing is mentioned here now. What it says, the pulse shape is plotted when there are 15 component modes. 15 different components of modes, okay, are summed with 3 modes active. 15 modes, component modes, are summed with the 3, like in the last diagram, 3 modes active. More modes are summed, the envelope becomes quite narrow. Okay, the envelope become quite narrow. It will be like this. The pulse appear to consist of single waves as more modes are allowed to exist. Okay, more modes are allowed, so it depends on the gain. Okay, the pulse shape becomes shorter, as I mentioned. That is why the shortest pulse produced have been from mode lock laser with the extraordinary wide spectral bandwidth. Output spectrum. Output spectrum is broad. You can get more longitudinal modes here. So if you lock it, you can get a giant pulse, and that is very short pulse. Example, ND-YAG laser. The spectral width is nearly or reasonably narrow at about 0.5 nanometer. With 0.5 nanometer, you cannot generate very short pulse. Okay, but ND-YLF and ND-glass have larger spectral bandwidth, about 5 nanometers. So minimum pulse duration that may be produced is 1 picosecond. So if we compress these, compress in the sense if we mode log these YLF and glass, then we may get 1 picosecond approximately. But in case of ND-YAG is very narrow. It's not possible. Here, when a laser with a larger bandwidth, such as dye laser, I explained many times in the class actually, with a very wide spectral width, around 100 nanometers. If you mode lock this kind of laser, pulses as short as 60 femtosecond may be produced. Okay, so we have more modes. When more modes are logged, then we get summed up. What we get, the pulse is a narrow pulse. Okay, so what is the conclusion? In case of mode locking, however, a large bandwidth is required. Don't try to mode lock some of the laser. You can simply use the K switch. Like if you have this much bandwidth, you don't need to go for mode lock arrangement. You can just use a K switch to get the pulse, because in any case you cannot get shorter here. Okay, pulse has to be a little bit like 5 nanometers, 6, 7, 8, 10 nanometers. Then you can apply the mode locking to get a shorter pulse, at least picosecond pulse. And then we can move also to the femtosecond, like in case of a dye laser, and now the femtosecond laser, which is TISAF, titanium sapphire lasers. And here, if you see the figure, there are many modes and overlapping and summed up. When they summed up, you get a very sharp pulse at the output. Okay, so this was the lecture about the mode locking, and it finishes the chapter 7.